Okay, welcome. We now continue with the second module, which is focused on short channel effects. And these are the contents. We are focusing on small geometry effects followed by MOSFET capacitances. And these are the prescribed textbooks and the reference textbooks. So this is what our focus is on: small geometry effects and MOSFET capacitances. So now we will consider the short channel. So the moment the length of the channel is made, the length of the dimension or the dimension of the channel is not going to remain as a rectangle. Instead, it will take the shape of a trapezoid. So that is what is shown. Shows the simplified geometry of a gate bulk depletion region and a PN junction in a short channel MOS transistor. So this is how it is going to change. So if you take out the trapezoidal structure, we get some dimensions. So this is the N type where you have the junction going to be formed, and this is called as the junction depletion region, which gets depleted, and this is the dimension or the depth of the junction. Xj is also the depth. Xdm, we will understand this later. Both are the depth itself. Delta L naught is the variation. L is actually the length of the channel, but delta L naught is something because of the depletion region being created. So we have few terminologies here. If you understand, you can represent them as a triangle, right angle triangle. So if you look at this mouse pointer being moved or here, it is just like a right angle triangle. Therefore, the Pythagoras theorem is applied here. Xj plus xdd, because xdd is the depth at the drain terminal. So look at this, students. This is at the drain and this is at the source. So normally we have a notation which is represented as xdd and one more representation given as xd capital S. So capital D and capital S represents the drain and the source, and D represents the depth. So the depth appearing at this particularly two terminals is given as xdd and xds. So xj plus xd whole square is equal to xdm square plus xj plus delta ld whole square. So applying like a Pythagoras theorem, we get this. Once you expand and you substitute, make it as a quadratic equation. So you get delta LD square plus 2xj into delta LD plus xd m whole square minus xdd square minus xj square minus 2 into xj into xd d whole square. Xj square has been removed, and that is how the equation has been substituted here as 0. Quadratic equation. Finally, solving, we get this expression. So delta LD is given by this expression. So please try to verify this. This is also implementing binomial theorem. I haven't tried, but please try to get this. So similarly, this is at the drain. Similarly, you get it at the source. Same way, xj, instead of xdd, it is xds. So I have not tried. Halfway I could, but I was stuck up. Something went wrong. Then I found out that binomial theorem you have to use. I have stopped. I have not yet proceeded further. So please check how do you get this, and ultimately this is the formula. Otherwise also the scope of this derivation can be neglected, particularly because this we are not still sure how much it is there. Therefore you can just go ahead by conceptualizing and understanding only the final formula. So the threshold voltage due to short channel effects is given by delta Vt naught 1 by COX into square root of 2q epsilon Si Na into 2 phi f into xj by 2L, and this is at the drain and this is at the source. So this is the representation for delta Vt naught. So as I have told you, we don't get the rectangular shape, we are getting the trapezoidal shape, and the drain depletion region is larger than the source depletion region. Yes, because the positive drain to source voltage reverse biases the drain junction, because you know the applied voltage is at the drain. You remember VDS less than VGS minus VT is where the potential is applied at the drain, and that is how we get the linear region. In case we apply the voltage at VGS greater than VDS greater than VGS minus VT, then it is the saturation region. So everything happens at the drain junction. Therefore, the drain depletion region is larger than that which is occurring at the source. So the bulk depletion charge in the short channel is smaller, and therefore the threshold voltage is modified, and it is given by this formula as already dealt in the previous slide. So VT naught is the zero bias threshold voltage calculated by considering the conventional long channel. So VT naught is what we get because of the long channel, and delta V naught is the shift or the reduction due to the short channel effect, and the difference of these two will give us the short channel effect. So we will now understand with the help of a problem. So it is the same problem. Considering the NMOS channel with the following parameters, we have substrate doping as 10 power 16 centimeter to the power minus 3, polysilicon Nd as 2 into 10 power 20, gate oxide thickness 50 nanometers. Earlier it was 500 angstrom units. It is one and the same. 500 into 10 power minus 8. So it is made as 50 into 10 power minus 9 nanometers. So now we will calculate VT. VT is from the conventional formula where we had the long channel effects. So using the conventional formula, VT naught is the zero bias threshold voltage. So the threshold voltage without the channel implant was found out to be 0.40. Our previous problem. I hope I am clear with this. This is because of the long channel. And the additional P channel implant will increase the threshold voltage. So the threshold voltage has to vary now. It has to increase. So VT naught is given by this much plus this formula. If you substitute, it is going to change like this as 8.855 volts. And XDS and XDD represent the depth of the PN junction at the source terminal and at the drain terminal, and respectively the expressions are given with these two representations. As I have told you, please remember these two expressions. So as per the formula, phi naught has to be calculated, which is given as Kt by Q into ln of Nd into Na by Ni square. This is substituted and it has been found out to be 0.76, and XDS and XDD is nothing but the junction depth at the source and the drain terminals, and this is given by 2 square root of 2 into epsilon Si by Q into Na into phi naught. Appropriately substituting, we get them as XDS and XDD as 0.314 micrometer. So now threshold voltage due to shift delta T naught has to be found out. So that has been given by the formula 1 by Cox root of 2Q epsilon Si Na 2 phi F into Xj by 2L, and this formula which we got with respective to the source and the drain junction depth. Appropriately substituting, we get them in terms of L. L is unknown to us, therefore we get the threshold voltage for the short channel as this 0.855 volts minus 0.19 volts divided by 1 by L. L is in terms of micrometers. So this is the formula as already discussed, and appropriately, yes, as calculated, if you have the drain voltage VDS as 5 volts, appropriately substitute that here in order to find out the depth. So that gives you this much 0.863 micrometer. XDD is the depth, therefore it is given as meters. So this is the resulting voltage shift can be calculated by substituting this formula. And if you substitute XDD and XDS as given already here 0.863 and 0.314, we get the difference delta V naught as 0.45. So this is the threshold voltage because of the short channel. It is VT naught is equal to 0.855 volts minus 0.40. Therefore this is the voltage of the threshold because of the short channel. So this is lower than so earlier what was it? It was in the range of 0.40 something. So it is lower than the threshold voltage predicted by the conventional long channel. So because of all these things, now we have concluded that the threshold voltage of an NMOS is given as 0.2 VDD, and for the PMOS it is given as minus 0.6 VDD. So of course we can take that parameters, but since we are learning about the threshold voltage, whatever the intricacies involved with the threshold voltage, right now when I simply told us threshold voltage, it was clear. But right now we all have understood that what are the different parameters which are involved in giving us the threshold voltage. It may be the work potential, bulk potential, charge, length, width, everything is involved in determining the threshold voltage. So continued with that is the MOSFET capacitance. So what exactly is the capacitances involved in MOSFET is the topic involved right now. And when do we generally require this? When we are looking for the AC response or the transient response. So parasitic capacitances associated is determined here. So most of these capacitances are not put together, they are distributed. So distributed means everywhere they exist because of the MOS layers. So that is how we need to understand them. And this is the diagram. So you have the gate, you have the diffusions, source and the drain. Everywhere there exists a capacitance. So this is the cross sectional. Wherever you have the oxide representation and a conducting material in the top and the bottom, there exists a capacitance. So we will identify the capacitances, and basically they are grouped into two categories: oxide related capacitance and junction capacitance. So in oxide related capacitance, always it is the oxide coming in there as the dielectric. In junction related capacitance, wherever a junction is formed, a capacitance is created and a thin layer of dielectric is also created. So we will now see what are the different categories of oxide related and junction capacitance. So if you take the DC model of the MOSFET structure, we have the gate, you have the body, you have the source and the drain. So okay, if you just transform this, so this is the substrate, this is the source, this is the drain, and this is the gate. So you can notice you have the capacitance between the gate and the source. You have the capacitance between the gate and the drain. You have the capacitance between the gate and the body or the substrate. You have the capacitance between the drain and the substrate, source and the substrate. So few parameters of the capacitances are shown here. So this is how we find the capacitances, and now we will focus on oxide related capacitances. And then we have something else called as overlap capacitances. So this is got due to the structural arrangement. That means one over the other you have the capacitances. So where exactly this capacitance arise are, these are called as CGD, that is gate and the drain and gate and the source. So assuming both the source and the drain diffusion regions of having the same width, it has been found out that CGS and CGD overlapping capacitances at the source and the drain terminal as COX W into LD. So W is a constant parameter with both the, almost with all the source and the drain terminals, where COX is given as epsilon OX by TOX. So this is the standard formula in understanding what exactly is the capacitance. So everywhere you have, since it is an oxide capacitance, it is involved with respective to oxide, which is COX given by epsilon OX by TOX. Now we will consider the capacitances got from the interaction between the gate and the channel. That is, gate and the channel. Channel is nothing but your N type or the P type, pole charge, majority charge carriers. So since the gate channel region is connected to the source, the drain and the substrate, therefore we can get the capacitances from the interaction between the gate and the voltage as gate and the channel as CGS, gate and the source, gate and the drain CGD, CGB, gate and the substrate. So these are the few more capacitances arising because of the contact between the gate and the channel. But generally CGS is actually gate to channel capacitance seen between the gate and the source. So what is source and drain? Once you have a channel, it's all together the same. The junctions have been broken, source and drain are connected, and therefore you have them together as either source or the channel or the drain. The gate to drain capacitance CGD is actually the gate to channel capacitance, same as I told. So CGD and CGS are equivalently channel capacitances. So, and now apart from understanding this, now we need to understand what exactly these voltages are in different regions. So the different regions we have already come across this are the linear region, cutoff region, and then the saturation region. So first region we will consider is the cutoff region. In cutoff mode there is no conducting channel. Yes, there is no channel. So the gate to source and the gate to drain are both equal to 0. Since there is no current, there is no conduction, therefore no capacitance exists, and therefore the capacitance is equal to 0. And still substrate is there. Therefore, CGB is approximated by COXW by L. Substrate is there. That is your semiconductor material. So, it has its own capacity of doing the conduction. Apart from that, the channel is getting created because of the voltage you are applying. So, the capacitance at the substrate is given by this formula COX into W into L, whereas CGS and CGD is equal to 0. This happens in the cutoff mode. So now we will have a look into the capacitance involved, or what is the status of the capacitances in the linear mode. In the linear mode we see that the junction is almost ready to be created and the process involved is inversion. Therefore the inversion layer is created. Almost the channel is created, it gets created by the influence of the gate voltage and the drain voltage, and limited amount of current flows from drain to from source to drain. So whatever is the amount of voltage has been applied, proportionately that much of current flows in this direction in this particular channel in the linear mode. Therefore and the inversion layer acts as a shield for the substrate. So substrate will have, since the channel is now created and it is conducting, the substrate is free from any of the electric field impacts. Therefore, the capacitance at the substrate CGB body CGB is equal to 0. Now we will have since the device is conducting, we will have only the source and the drain capacitances involved with respect to the gate. Therefore, the distributed gate to channel capacitance is given by the formula CGS, which is equal to CGD, is given by half of COXW into L. So earlier in cutoff, everywhere it is absent, CGS and CGD is 0, but only the substrate capacitance is working, it's there. Whereas here the substrate capacitance is 0 and the capacitance of the oxide source and the drain is given by half of COX into W into L. Next we see at the saturation mode. So apart from inversion layer, the channel is created and finally you give more and more of your drain voltage. Because of the application of the drain voltage only at the drain terminal, the channel gets pinched off. So drain terminal is completely away from not working since it is pinched off. It is totally lost its contact. Therefore CGD is equal to 0. But still the source is there, it is linked and it is conducting. But it is not reaching to the complete drain terminal because it is completely pinched off. Only the limited current flow occurs. In spite of increasing your gate voltage and the drain voltage, there will have no impact on the current. So the saturation, that is why we call it as a saturation current, same amount of current flows. And here also the gate to substrate capacitance is 0 because the channel has shielded the substrate. Therefore, we have only CGS. So the CGS here is given by 2 by 3 COXW by L. Now at the source only, drain is also 0, substrate is also 0. So this is how the capacitances exist in 3 different regions: linear, cutoff and saturation. So this is the summary of our capacitance status. So initially in the cutoff, all the capacitances CGB is there in cutoff. So it is COX W by L. CGB capacitance is there, whereas in linear and in saturation it is 0. Whereas CGD, this is CGD in cutoff. CGD is also 0 here, and CGD in linear is this much. CGD in saturation is COX W by WLD. CGS, CGB. Okay, this is how the capacitances exist in the different regions. Next we have the junction capacitances. So one is the oxide capacitance and next is the junction capacitance. So this is happening wherever we have the junctions. So voltage dependent source substrate we consider, and drain substrate junction capacitances. So we have one capacitance at the source and at the drain with respect to the substrate. So this is seen from a three-dimensional diagram, and if you look, this is how the junctions are seen. So you have one junction here, 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 everywhere. So 1, 2, 3, 4, 5 are the different junctions existing in this model. So this is the junctions. They are formed in respective to XYZ direction. So we have width, we have W, and we have the depth XJ. So this is how the depletion capacitances can be calculated using the formulas XD and phi D, which we have already understood, and capacitances are calculated using this formula. So if any much more problems are to be discussed, you can refer to the textbook by Digital Design by the author Sung Mo Kang. So that gives you the entire information about the junction capacitances. Almost we have reached the end of this topic. So with this we complete second module.